Okay, good afternoon, ladies and gentlemen. This is Professor David J. De Los Reyes. What I will be discussing tonight, this afternoon, is actually the current consumption of a three-phase motor, whether the connection is Y or delta. So what I will be proving or bringing out this afternoon is actually the general formula and how to compute. Okay. Sorry for this one. The general formula and how to compute. Sorry for that one. I missed one term on the formula. Sorry for that one. For the current consumption of a three-phase motor, whether the connection is Y or delta. And this will be the required formula. So I will now try to prove that whether the connection is Y or delta, the formula and how to compute for the current drawn by the three-phase motor will be given by this formula here. That is, line current is actually P, capital letter P meaning the total true power in watts over the square root of 3 times the voltage line to line. From line 1 to line 2, that's a voltage line to line, times the line current, times the power factor. Okay, let's proceed. The title of the topic will be three-phase motor current calculation. So this will be the setup. Okay, that will be the setup. So I have here a figure here. To specify a motor, just draw a circle here, then place letter N, that will be N. It refers to a motor. And the lines coming out from this one is actually three. It's three-phase, right? Line number 1, line number 2, line number 3. So if this motor here is plugged into a three-phase source, this motor here will try to draw the line current, the so-called line current. If we say a three-phase motor, the three line currents will be the same. So I didn't place any subscript here. But there should be IL1, IL2, and IL3 because they are all the same. I just place it as simply I sub L. Okay? And to compute for the current consumption IL, meaning IL1, IL2, IL3, which are all designated by I sub L, we must have to use this formula here. And the proof of this one is actually this. Okay, I will try to discuss. Supposing the connection of the motor is Y, the internal windings are actually connected in Y. This is Y. Could you see it, guys? It's Y. I'll try to zoom it a little bit. Yeah, that's Y. The one on the right side. This motor here, first condition, if it is connected Y, this will be the configuration. So if we try to place the designation of the parameters, this is IL1, IL2, IL3, okay. Phase number 1, I place it I with a zero like this, meaning phase. So phase current number 1, phase current number 2, phase current number 3. Right? By inspection, the line current and the phase current for a Y connection are actually the same. So I place it here. The line current and the phase current for a Y connection are actually the same. Could you see it, guys? Oh, it's on the bottom portion. It's on this. For a Y connection, the line current is equal to the phase current. So there's a relationship, line current is equal to phase current if the connection is Y. Okay? So let's now try to derive the formula on how to compute for the current if the connection is Y. The general formula is given by this one here. Total true power is actually 3 because there are 3 equivalent windings, right? Times the voltage per phase, times the current per phase, times power factor. So if we now try to consider a Y connection, okay, voltage per phase in terms of line voltage, because if we are given a motor, what is actually given is the line voltage. So to compute for the phase voltage, this is the phase voltage across one winding. It will be given by the relation, actually for a Y connection, there's a relation for the phase voltage and the line voltage. And the line voltage is greater than the phase voltages. And the relationship is actually voltage line to line is actually square root of 3 times voltage phase. This line voltage here is greater than the phase voltage by a factor of square root of 3. Because they are displaced from each other 120 degrees. So instead of twice the voltage per phase, it should be only a factor of square root of 3 times voltage per phase. So going back to this formula here, we could replace this voltage per phase for a Y connection. By the line value, it should be voltage line to line over square root of 3. Okay, times the current per phase. But by inspection, the current in each phase is the same as the line current. So actually this current per phase is still I sub L. Okay? They are the same. So this is I phase is actually IL for a Y connection. That is relationship number 1 for a Y connection. So this is multiplied by power factor. So actually if we try to simplify this, what will happen? I will try to continue here. There is a 3 here. Right? But 3 could be written as square root of 3 times square root of 3. Square root of 3 times square root of 3 is actually 3. Okay? So this square root of 3 here cancel with this. Okay? So what comes out now for the total true power will be square root of 3 times the product of the line voltage times the line current times the power factor. That is for a Y connection. So actually what we derive is actually this one here. Right? So if we now try to compute for the line current for a Y connection, line current now will be the total true power in watts over square root of 3, algebraic manipulation, times the line voltage, sorry for this one, square root of 3 voltage, this is times power factor, times power factor. Okay, actually this will now be the total line current if the connection is Y, that is, as was derived from this, I've shown you that's the derivation. Using the relationship of the line current and phase current and the line voltage and phase voltage. Square root of 3, voltage line to line, I line times power factor. So if we try to compute for the line current, it will be true power, total true power over square root of 3, voltage line to line times power factor. Okay? So this is the general formula on how to compute for the line current if the connection is Y. And to prove that the same formula also applies to a delta connection, okay, we shall now consider a delta connection. And we shall bring out the relationship of the phase current and the line current and the relationship of the line voltage and the phase voltage. I adjust my camera. Okay. Let's now try to consider the motor if the connection is delta. So this will be the delta connection. So this is delta connection, this is delta. First winding, second winding, third winding. So if we try to place the designations of the parameters, this is current, phase current number 1, phase current number 2, phase current number 3. This is line 1, right? So IL1, this is line 2, so this should be IL2. This is line number 3, so this will be IL3. So the relationship that we could derive from this is actually what is the same here. For a delta connection, the line voltage is actually equal to the phase voltage. Okay? This is the line-to-line voltage, and this voltage here is actually same as this voltage here. And that is actually phase voltage number 1. So for a delta connection, whether we like it or not, the line voltage is actually the same as the phase voltage. So this will be the first relation that will be needed. And how about the current? For a delta connection, the line current is greater than the phase current because considering line current number 1 here, this one here, it will be the summation of the current coming out, okay, considering this junction. There are two currents going out, right? Going in, coming out. So this line current is here is actually this vectorial sum of phase current number 1 and phase current number 2. And the relationship that will come out here is that the line current will be equal to square root of 3. It's not times 2, right? Times the phase current. No, times the phase current. So for a delta connection, this is the relationship of the current. For a delta, the line current is square root of 3 times the phase current. Okay? But for the Y, actually originally, the phase current and line current are actually the same, right? But for a delta, the line current is square root of 3 times the phase current. So again, if we go back to the formula, this one here. Okay? If we try to follow that one, total true power now is equal to 3. 3 can be written as square root of 3 times square root of 3. The phase voltage for a delta connection is same as the line voltage. Okay? So this is multiplied by, instead of phase voltage, since they are the same, in terms of line voltage, this should be V sub L. The current per phase for a delta connection, it should be, if we try to compute from this relationship here, it should be the line current over square root of 3. So this is multiplied by a line current over square root of 3. Could you see it, guys? Times the power factor. Actually, we are solving to the total true power consumed by a delta connected motor in terms of the line voltage and line current with the given condition, that is line voltage equal to phase voltage and line current equal to square root of 3 times phase voltage if the connection is delta. So actually, this is square root of 3 here. Cancel with this. So no more square root of 3 at the bottom. So what will come out will just be simply square root of 3, the product of the line voltage, line current, times power factor. That is total true power consumption for a delta connection. So if we now try to compute for the current consumption for a delta connection, okay, as you can see it, it will be true power. The denominator will be square root 3, okay, times voltage line to line, times power factor. It is the same as this one here. So I have shown you that the formula on how to compute for the line current, which is the same for all the three lines for a balanced motor load. It is given by the formula line current equal to the total true power in watts over square root 3 times the value of the line-to-line voltage, right, times the power factor. So if you are given a motor in which the true power is given, you are given the line-to-line voltage rating of the motor, and if the power factor of that motor is not given, you could assume 80% or 85%. But if it is given, power factor should be given. Okay? So by using this formula here, the right formula, the line current will be, like what I said, it will be the total true power over square root 3 times voltage line to line times power factor. This is in amperes. So the significance of this topic here is that whether the motor is connected Y or delta, the general formula and how to compute for the line current, which are all the same in all the three lines because the motor is balanced, it will be given by this formula here. It will be line current will be equal to the total true power over square root 3 times voltage line to line times power factor. And this is in amperes. Okay, that's it, guys. Good afternoon from Los Angeles. This is Professor David J. De Los Reyes.